everyone to the Non-Commutative Geometry Seminar, the Global Non-Commutative Geometry Seminar. We're going global today because our speaker, Teun van Nuland, is in Sydney, where it's 5 in the morning. When we are done, it will be 6 in the morning, and the sun will be rising, and it's going to be a beautiful day there. So he has that to look forward to. But in the meantime, he will tell us about cyclic cocycles and one-loop corrections of the spectral action. Please.
Thank you. And on this beautiful morning, we will be looking at the crossroads between mathematics and physics. So I hope my audience is interested in at least one of those. So it's going to be based on some joint work I've been doing with Teun van Nuland at Radboud University Nijmegen. We've been doing since the second half of my PhD thesis. Teun van Nuland was my PhD supervisor. And actually now we're still working on this because we see this as a new strengthening of the link between non-commutative geometry and quantum field theory, in which we see a future. And we've published 3 papers. Well, at least the third one is in press. But the second one is actually in a physics journal of high energy physics, which I can recommend to anyone because they don't expect you to give any proofs. It's very convenient. But we wouldn't be true mathematicians if we weren't also interested in the proofs and the nice a rigorous underpinning of our work. So that's kind of what we did in particular in our last paper. And in particular, we're giving also a precise mathematical definition of these graphs, which suggestively look as they should do, like Feynman diagrams. So we will get to that later on in the presentation. All right, let me do this. But first, some introduction, because what we're going to talk about today is the spectral action. That's going to be the central object. And so given a spectral triple, AHD, the spectral action is given very simply by, so mathematically it's very simple, by the trace of f, some cutoff function or any other nice enough function such that this expression is defined, acting by functional calculus on D, the generalized Dirac operator. And this thing is so mathematically very simple, but physically also kind of important. And why it is called the spectral action? Well, because it depends on the spectrum of D, including multiplicities of the eigenvalues. D, of course, is compact resolvent here. And that's what I mean by a spectral triple. So it has a basis of eigenvectors. And it has countable eigenvalues. All right, so for any unitary U, you can conjugate this D. And then you can put out the U's. And then you can use cyclicity of the trace and you see, oh, nothing has happened. Where does the physics come in? It comes out if we perturb D by a 1 form, which in physics you would call a gauge field or a gauge boson maybe. And V is given by AJ, commutator D and BJ, where AJ and BJ are in the algebra, so that's where the algebra comes in actually. And H also comes in here because otherwise we couldn't make sense of the commutator here. D BJ minus B D BJ D. This commutator is defined because they both act on the same Hilbert space or in the same Hilbert space. All right, and then we can look at the spectral action again for this fluctuated Dirac operator. So it's just given by this, and then what do you get? that's going to be like central in the talk today. Yes, and why do we take this weird form of V? Why is this a one form? Well, it's a sort of generalized one form, con-differential one form, you could say. And AG, in the commutative case, when the spectral triple is just given by a manifold, then AGA could be a function, FJ, and BJ could be a function, GJ. And this commutative D is one way to generalize the round differential D. So this is actually a one form on manifold. And it's very nice if you are a physicist and you know that gauge fields are actually Lie algebra valued one forms. Well, you can also do this. You can have, because AJ can be in an algebra. Yeah, you can also use some matrix algebra over a manifold, and then you can get gauge valued one forms. And it goes even beyond that, so you can have non-commutative space in a way. Now, historically, there have been two ways to make sense of the spectral action, to expand it and get out some data. So the first way is, yeah, it's kind of the heat trace expansion for the spectral action. What do I mean? I mean, you just replace D by D over lambda, and then you expand it in lambda as lambda goes to infinity. And now for a specific Dirac operator, which is given by a very specific spectral triple, namely, as I just said, a matrix algebra over a manifold, then the Dirac operator for M, the manifold, times F, the finite space. If you calculate the spectral action in this way, lambda going to infinity, then you can write this as a tonic expansion. And the terms here are familiar to physics, so this is a Einstein-Hilbert action, so it gives gravity. And here you have Young-Mills, so it gives particle physics and even the Higgs field, if you like, if this phi is interpreted as the Higgs field. Yeah, so it's a very beautiful way to get out the standard model of elementary particle physics from a very concise mathematical theory. This specific spectral triple that I'm talking about is not falling from the air. It's just it's really given by some generalization of Heisenberg's formula in some work of Shamsin and Kohn. I don't remember the year, but right. Now, how do you really get the physics out? If you want to test such a theory, then you will need that the constants will be renormalized. So the thing here, I said, yeah, this is familiar to physics. What I meant is you get the integral over the standard model Lagrangian. But the Lagrangian, that's a classical object, and it's taken in quantum field theory as a starting point to derive a quantum field theory and get some physics out of this. And the way you do this is by using the renormalization group flow, and this is a very well-known quantum field theoretic procedure, but it's maybe not so rigorous for a mathematician. So it's kind of not so nice. And also we started with really the spectral triple, which of course there's a very nice reason to do so. So there's like this philosophy behind it, that you have a spectral action which is purely spectral, and you have like a non-commutative generalization of space, which is very nice. And then when we do this, that's currently the only way to get physics and physical predictions out of non-commutative geometry. We kind of give up on the spectral picture. We kind of, yeah, we are really using the manifold, and actually you can only do this for flat space. And you use non-rigorous techniques. So the question becomes now, like, can we also get physics out of non-commutative geometry in a spectral way, so that you have really a nice mathematical formalism for this? All right, that's a grant project, of course. But this brings us to the next way, the second way to expand spectral action, which is expanded directly in the gauge field. Of course, for the first step, if you want to get physics out, you first expand in lambda and then you expand in the gauge field. But in the second step, the second way to expand the spectral action is by doing this directly without using this heat trace expansion. And of course, this can be done. We can write a Taylor expansion, because this D is just additively perturbed by some phi, and phi is bounded. And then in certain cases, for a nice enough F, depending on the summability of D, then you can actually say that this symbol becomes an equal sign, and that this really converges absolutely under the right conditions, and that this thing in the trace is actually trace class. So there's some nice functional analysis behind this, which I will not really discuss today, unfortunately. This is really in the first paper we talked about. And but there is a second problem, you could say, that you first have to solve, namely, besides asking whether this higher order derivative of f of d plus dv is trace class, besides that, you have to ask, what is it? And here it becomes important that d and v do not commute in general. So what is this? What is this thing? Yeah.
Can I ask, shouldn't there be
Yes.
a v to the n in this formula? I mean, in Taylor's formula, there should be some v to the n, right? Something like it.
Sure,
Yeah. That's kind of the goal of today, actually. Yeah.
Right.
Oh, okay. So it's missing
Yeah.
here, but you're going to put it back.
Right.
Kind of, yeah. Yeah, the problem here with writing v to the n is what usually you're gonna get is something like...
No. I think he's right, because he's taking t equals 1. So it's really f of d plus v. So it's okay.
There is no need, yeah.
There is no need, because it's t is equal to 1, because it's d plus v. It's not d plus tv.
Mm-hmm.
So it's really t equals 1. And so the formula is okay.
Yeah.
Well,
But what I wanted to say is that you would maybe expect something...
Yeah. You could have
like
put
that.
f of d plus sv, and then you'd have an s to the n. But s is 1. Okay. No, it's okay. It's fine.
Yeah, okay. But one other thing that I wanted to stress here, which is good, is that you would maybe expect this thing, but you cannot get this from this higher order derivative, because you would get, for instance, if f would be some resolvent, maybe x minus I inverse, then you can compute this, and for instance, ddt of fd plus tv. What is this? All right, maybe I don't know if I can do this. If I I'm not making any mistakes. Well, anyway, whether this is correct or not, you're gonna get some functions of D and V, and they come up in a symmetric way, of course, and because they don't commute, you cannot write V on the left always. Of course, for the first order term, you can kind of cheat because you can always commute V to one side. All right, that's what I wanted to say because that becomes important later. All right, can I clear all drawings? All right. So that was the introduction, and now we're really going to first go to the mathematics and then go to the physics in 2 parts. First part, the expansion of the spectral action. So, all right, can you read this? Because for me, there's something in front. All right. So suppose that we have a S-summable spectral triple. S can be something that's smaller than the dimension of the manifold, for instance. But it is very general. This is a very general thing. It can be any S-summable spectral triple. Then let us denote by omega n over A the algebra of universal n forms over the star algebra. So in particular, that means that omega 0 of A is just A, and this D is universal. This is what I write for the universal differential. Some people would write delta. It's just given by 2 relations, namely, you just have to ask that D squared is 0. And you go from omega n to omega n plus 1 to omega n plus 2. Then nothing comes out. And you ask that it satisfies the Leibniz rule, DAB is ADB plus DAB. And you can give a representation of omega 1D of A, which is this differential one forms that the differential one forms that I talked about already, where commutative of D replaces in this case universal differential. All right, you can also do is you can give a representation for any omega n of A on the Hilbert space, but this becomes less nice because then you have to keep track of the differential. So 2 days ago, I had a discussion with Adam Rennie, and he was like, no problem at all. But in a way, it becomes much more difficult if you want to work with the represented ones, because to get a differential, you have to do some work, mod out some space of jump forms. All right, it's nice for us to just work with universal one forms, because you know you're not throwing away any information. And then we are representing it just for NS1. And our goal now is to expand the spectral action like a Taylor formula, but not quite a Taylor formula, because we want to expand it in this universal one form. So not throwing away any information. And see if we can get some powers of the universal one form, some expression of this involving A and dA, such that we can give some gauge theoretical interpretation of the spectral action in this way. All right, this is a bit clear. Is the goal clear for everyone? Are there any questions?
Yes, I have a question, Tom. So what is the classical analog of that D plus V term? I mean, D, of course, is Dirac, but classically, what is D plus V?
Yeah, it's when you, as I said, a gauge field. I don't know what you mean.
Well, no, I think I know the answer. I mean,
All right.
the point is that D plus V is the Dirac operator in the gauge field V. That's what it is. And it's exactly correct because the V, when you define the V by commutator with the Dirac, what you get is not the differential form. What you get is the Clifford action of the differential form. And that's exactly what we need.
So it has to be interpreted as Clifford multiplication.
But D by itself contains Clifford multiplication. The operator D is Dirac operator, so it contains a Clifford multiplication, so you don't have any problem.
I mean, in the Dirac, there is already gauge field.
No, in the Dirac case, if you perturb it like he explained, then what you get is the usual gauge fields.
I mean, in the Dirac, we have I gamma mu D mu plus, you know, the
Sure, but when you permute with functions, what you get is only the gamma mu corresponding to the electromagnetic field.
I see. So this is it only for electromagnetic field, or
no,
can
because if you take matrices or if you take a bundle, then you will get the corresponding gauge field.
For non-commutative ones as well.
Yeah.
You do have to assume something on AG and BG usually.
Yeah, that's okay.
That it's self-adjoint and
yeah, that's okay. Those are okay. I was just wondering about the classical interpretation of this term D plus V. I mean, okay, yeah, fine, good, thank you.
Yeah, you can work it out. So electrodynamics is a good example to work out, and then you have 2 by 2 matrices. Yeah.
Okay, very good.
Yeah,
Okay, good, thank you.
Yeah, because here D indeed includes this gamma matrices, so they come up here. Yeah.
Yeah.
So V also contains gamma matrices. All right, I hope the answer by Con is sufficient because it's better than any answer that I could give.
Yes.
Okay.
we can discuss later also. Thank you.
Yes. All right. All right, to give some examples of universal forms, one very important example of a universal two-form is F, also called the curvature or the field strength. And it depends on A, it depends on any universal one form. In this way, you can define dA plus A squared. What does this mean? Well, of course, the one forms are given by sums of AJ, D, BJ, right? So for a simple example, if we can leave out the sums, this is no problem, of course. You can leave out the sum, and then yeah, it's written in AdB, and then if you act with the universal differential on this thing, you can use the Leibniz rule. So then we get dA dB plus A d squared B, and d squared B is 0. So you get dA dB, which is the first term here. And A squared, you can write it in this way. And let me also mention that omega 2 of A, forms can always be written in the form like A dB dC. But sometimes you don't know what C is. So in this case, AdB can also be written with all the universal differentials on the right side, and then with all the algebra elements on the left. But first you have to need the Leibniz rule. So you need to, from dB times A, you need to go to D of BA. And then you have to correct for a term. So you also get AB dA dB with a minus sign. So that's just to stress, like, this is correct, but it can also be written in this standard form. And another very important example of universal forms, universal n forms where n is n is odd, is given by the Chern-Simons forms. And this is also if A is ADB, then this one is also this huge string of ADB, ADB, DADB, etc. All these A's and B's and D's in some string, and you have a very large sum because this power k, you have to expand this, and then you get this whole string. And then this is just a polynomial in T, right? So you can just, this is just a trick. You can just integrate over dt and plug in 1 and 0, and then you get like this really sum of all these weird terms, and then you see that it's a universal 2k plus 1 form. But this is just a trick to give a nice contained definition of the Chern-Simons forms. And you can work out the examples. Was there a question?
May I have a question?
Yeah.
So should I think of A as a connection, one form of the connection? Yes. And F is like a curvature of this connection.
Yeah. Then F is curvature. Yes. Yeah.
Okay. Thank you.
Yeah. Yeah, it's a curvature of a connection. Yeah. But it can be more general in non-commutative geometry. So for k is 0, then Chern-Simons 1, you can work this out. You take k is 0, so you only have a. This is a trivial, it's a constant polynomial, so you just get a. Chern-Simons 3 of a, then you have k is 1 here, and you have t ada plus t squared a to the third. And then if you integrate that polynomial, you get 1/2 ada plus 1/3 a to the third. And as you can see, it gets more complicated each time you increase k. All right, so, but these things are very important also in physics. In the commutative case, if A is a connection indeed. Or yeah, equivalently a gauge valued one form. Lie algebra valued one form. And then these Chern-Simons forms, they come up in certain quantum field theories. All right, but they will come up later in this presentation as well. Now, let us finally get back to this Taylor expansion. And you notice I've taken the 0th order term of the Taylor expansion on the left. This is kind of to make it a little bit provocative for the people that work on non-unital spectral triples. So I encourage those to really have a look at these things and try to see if they can generalize everything I'm saying in this talk to the non-unital case. But another way to see the left-hand side is like the fluctuation of the spectral action. Just the fluctuation when you perturb it by this gauge field. Then you can write it again as a Taylor expansion, and if f is nice and it converges. And you can actually calculate it. So as I said, I'm not going into the functional analytic details, but I'm interested in the algebra. So like how you can actually write this. And as I said, we cannot put all the v's on the right-hand side. You always have some sandwiching between this bounded operator and then some function of the unbounded operator, and then bounded, and then function of unbounded, bounded, function of unbounded, etc. And you have to have some integral over these functions of d essentially, and f also comes in. And we get f prime here because we have kind of cheated at the first order. So if n is 1, then you can kind of cheat because this d and v do not commute, but the trace is cyclic, so you can always write v on the right-hand side. And this is what you use here. But it only works up to one order, and then you have to really use something like this, where you have these this integral. And if you have this form, what you can do to do some algebraic manipulations, we first want to define some extension of this, some multilinear extension. So this thing, which I call a bracket, is a multilinear extension because it's multilinear in the arguments. And it's also cyclic in the way that, you can move the arguments to the left cyclically, and then because of the trace here, then you can move it. Right here, you also have a contour integral, so it's a bit hard to see. But then you get actually, if you put in again all the same v's, then you get the terms in the Taylor expansion. Now I can write any formula here actually. This is not the only way to write an nth order derivative of the spectral action. You can also maybe write it like this. This is sort of a Dyson series. And so the precise details are not important right now. The point is, so delta n is a simplex that S, such as S0 plus up to Sn equals 1 with the standard measure. All right, but the point is, again, you have sandwiched, oh, sorry, this should be V, not V1. This should be V, not Vn. But the point is, you can always do this in any way that you can, like write this thing. You can also define this multilinear extension. Why is this the case? Because of multiple operator integration. So this is just a general way to denote, all right, we have some way of writing an nth order derivative of the spectral action, or an nth order of a operator function in a way of an integral over these v's with that are sandwiched between functions of the unbounded operator. All right, so yes.
If you are saying for suitable f, you mean something like decreasing rapidly, yes?
Yes, certainly.
Something like that, okay.
Yeah, so a typical example is the Gaussian. So f of t is e to the minus t squared, or maybe t squared over lambda if you want. This is a typical example, but it can be more general. Sometimes you want a Schwarz function. Sometimes you want something just that's k times continuously differentiable, and that's the case more rapidly than inverse polynomials up to a certain degree.
Sorry,
so it depends on your results, what you want, what you have to assume on f. Yes?
But sorry, do you really want to include this constant gamma in this definition of f?
This
After
lambda.
all, then lambda is running, yes?
You can take lambda as one. Yeah. I'm just saying you can take any function for f. That's just, so you can take any lambda, and then this will be a nice enough function. That's all I'm saying here. Yeah.
Yes. For this I agree, but after all, if we would go back to this previous slide for this expansion in power of lambda, then f is fixed and lambda is separate parameter. That's what I meant.
But I mean, in physics, they would always put lambda, because without lambda, it doesn't even make sense. Because D has units, I mean.
Yeah.
Yes, exactly. The reason for the lambda is simply that when you want in physics to apply a function to something, this thing should be dimensionless.
Yes.
And that's why we always put d over lambda, because d has dimension of an energy, and lambda has also the dimension of an energy. So this is
I'm trying to kind of speak with two tongues right now. Like I'm trying to speak physics and mathematics at the same time.
right. No, I think just go ahead. I mean, that's enough.
Yeah. No, good. Thank you. And we also introduce some other notation, because this is a cyclic thing, and it's given by like functional derivatives of an action. So in physics, again, speaking with two tongues. So again, you can define this. You can just give a different notation for this. And it also shows you that this bracket depends on f. And it's reminiscent of a one vertex Feynman diagram. And the only reason is only reason that I want to give right now is that, all right, this is cyclic, so you can define it like this, and there's no problem in notation. All right. Any questions? Any other questions? No, okay. So we've talked about universal n forms. Now, if we would like to see them appearing in the spectral action, well, the spectral action is just numbers, kind of. So you have to integrate universal n forms in a way to get numbers. How to do this? I would say the cyclic. Let me put on. My battery is running out. All right, saved. I would say cyclic cocycles are the natural way to integrate universal forms. And for this presentation, you can just say that a cyclic cocycle phi is nothing else than just a linear map, which I denote integral phi, from universal n forms to C. And for those who know a little bit more about cyclic cohomology, they know like these are these things. So it's a list, and you have these operators B and B. Well, I will just refer to the book of Alain for this. It gives an entire cohomology, which is very interesting, and many people are studying this. And what we want to do is we want to see if we can extract some universal forms that are integrated over cyclic cocycles. So first, we can just naively just define something, which we can see at least this thing will be well defined. You can replace this DAI by a commutator of D with AI. Sorry, this is subscript and this is superscript. So this should be subscript. Sorry about that. But now this is well defined because this universal D satisfies the Leibniz rule. So in this sense, it should be well defined, but this also satisfies the Leibniz rule. And from the definition of the bracket, we can derive two essential properties. The first one I've already given. This is just that this diagram is well defined. It only depends cyclically on the arguments. And the second one is what we call word identity. But it can be just derived from the Duhamel formula. Or it can be said that this is just this is one property of the multiple operator integral. In any case, you can derive this one. You can move A from from one place to the next if you pick up this d comma a, and then this bracket will be 1 degree higher. Now, we only need these two properties. You see, in many of the things that we try to do, we only use these two properties. These are really the essential properties. And you can use only these two to derive this form, this chain, or this cochain, is actually defined as a cyclic cocycle.
By this you mean it's in the bicomplex, it's with B and capital B, it is closed. That's what you mean.
Yeah, so yeah, if you act with B plus B,
yeah, okay, sure.
0, yeah.
Yeah.
That's what I mean, yeah.
It's not cyclic cocycle in proper sense, as Alan means, yeah.
There are
well,
kind of two, yes,
it's a cocycle in the BB bicomplex.
Yeah, in the BB bicomplex.
Formulation, but okay, I mean.
Exactly.
There are two definitions of cyclic cocycles, right?
Yeah,
And you can change between the two.
Sure. But what you mean is in the bicomplex. It's important
Yes,
to
I
say
mean
in the bicomplex. Forms
yeah,
the cyclic
I always
cocycle
mean
in the bicomplex.
Yes, okay. I always mean bicomplex, yeah.
Yeah, sure. Anyway, it's clear because you have a sequence, so.
Yeah. All right. So this is for all the even parts of this phi, and then we can also use the odd parts, and then we have to rescale this thing, and we have to add half, and then you add this universal differential here, which you can do for any universal n form omega.
Mm-hmm.
So you can define this other linear function on the universal n forms. And it turns out that this is also a cyclic cocycle in the bicomplex. If you take this contact constant here, see, yeah, this is just some formula that decays as k goes to infinity. All right, any more questions?
Have you, at this point, have you recovered the whole information somehow? I mean, you have the even part, okay? And from the other one, do you recover the odd part entirely, or do you? Yeah, because I see that you have integral over phi n over omega, and since you have the other one, yeah, so I think this is okay. Yeah, okay.
I think you recover everything, right?
Yeah, you recover everything. Okay.
Yeah. All right. So yeah, in a way, you have rewritten everything in terms of this two cyclic cocycles. So you have separated it in a nice way, such that both are cyclic. Yeah.
I understand. Okay.
Yes. Now, a kind of trivial or very important consequence of this two properties that we always use is that you can just shift the second one, and then you see that if you move a from the right of a comma to the left of a comma, then you can do that, but you have to always keep track of the commutator between D and A. And what happens here? So this is just by definition, really. So AD comma B, that's by definition phi 1 of ADB. And here we are assuming, just for simplicity, that A is ADB. Now for the second one, you have to do a little bit more work, but you can always also do this. So you can move this A for this. If you just look at this plainly, then you do not see any definition of phi entering here. You first have to, let me go back to the definition. Yeah, you first have to write it in terms of brackets where you have all these commutators on the right, and on the left you just have this one algebra element here. So this is not yet of that form, so you have to do something. You have to commute A with the comma, which you can do. You can just pick up a commutator, dA. And for that term that you then pick up, that's precisely phi3 of ADA. Because remember, this is AdB, dAdB. So this is defined, just by definition, phi3 is the term that you pick up. And the other term that you are left with is AD, BA, dB. And for that, you can use the Leibniz rule to shift the commutator with D a bit to the right. And then you pick up a term by the Leibniz rule. But then you can use phi2 again, using the Leibniz rule in reverse. So what you get is, here A squared is AdB, AdB, which can be written in this standard form as I told you. So it is phi2 over A squared is actually defined in that way, but you have to use the Leibniz rule. But once you have commuted this A over the comma, then you can always do this. You can always use Leibniz rule for the commutator and then use Leibniz rule for the universal differential back again. And then for the third bracket, you can do exactly the same thing. And the wonderful surprise is that you end up with something that is completely dependent on A and dA. This is maybe not trivial because, of course, you would end up with something in terms of A, B, dA, and dB, some huge string of those, but you can always write it in terms of A and dA. And this was something that was very nice when I wrote out this, and I had an entire page of all these AdBs, and it turned out to be just very simple formula. And what have we just computed? These are the terms in the Taylor expansion of the spectral action. So remember that the fluctuated spectral action is given by this thing, because it's just V put in this bracket, plus half of this thing, V, V, plus 1/3 of this thing, V, V, V. And it's given exactly by this one. And you can do this, you can repeat this, and it turns out that you get Chern-Simons forms here. And you get powers of the curvature here. So I see that I don't have much time left right now. So it's...
Since it is morning for you, please take your time, you know.
Yeah. We interrupted you many times.
Right.
So this is, these are actually entire cyclic cocycles, and for a nice function f, I will leave out the functional analytic details. But yeah, you get out this very clean formula. So you just get the Chern-Simons forms, which I talked about, and powers of the curvature, which I talked about. And for k is 1, you just get the curvature. For k is 2, you get actually the Young-Mills action in a way.
But here you forgot the t. I'm sorry. On the right hand side, there is no t. There should be a t. There should be powers of t.
Yeah, there should not be a t. Oh,
so there shouldn't be a t on the left.
Yeah, I thought I corrected that one actually. It's still there. All right. Yeah. Thank you. Okay. But what is this importance of this formula for physics? Well, the importance is that these cyclic cocycles, you have to think of them sort of like the constants in the standard model Lagrangian, which you can then try to renormalize. So these cyclic cocycles you would like to make quantum and then see what comes out. See if you can change this and then change a classical spectral action into a quantum one in a way. So that's what we're gonna do. We introduced the following notation as earlier. And this represents a non-commutative vertex in the sense that if this f goes to unit function, constant function, then this would become commutative again. But as it stands now, you cannot commute any of these vi's. So it depends here, opposed to normal quantum field theoretical Feynman diagrams. You cannot, it matters where you connect these gauge fields to and in what order you connect these gauge fields to the vertex here. This vertex, of course, is non-local, and the non-locality is really given by f. All right, then we can have a look at again at the Taylor expansion written in terms of the brackets, and we can, just for intuition, look at this these diagrams. Yeah, so this is just an expansion of one vertex non-commutative Feynman diagrams. Yeah, with no loops. So it's
so 1 over n is just the cyclic symmetry, and this is a normalization due to the cyclic.
Yeah, you could also put it in the brackets.
You could put it in the bracket, but it's nice to leave it out and have it from the cyclic symmetry. Yes, yeah.
Yeah, that's the reason. Yeah. But now this already gives you some physical definition of what you should do to get a renormalized spectral action. You have to work out what happens if you also include more diagrams. What happens if you also include diagrams with loops? So we first have to define what this means, a diagram with loops. So we wish to incorporate this. And yes, I'm leaving out functional analysis. So let's say the gauge fields are all matrices with respect to the eigenvectors of D. So we kind of look at the finite dimensional case here. So an HM is Hermitian matrices with respect to the eigenvectors of T. So all the eigenvectors up to M. All right, how do we define this? We use a recursive definition to define Feynman diagrams with more loops. In the sense that we assume that a Feynman diagram is given with a certain amount of these curly lines that do not have a gauge field attached to them. So you can always count how many lines there are, these internal lines. And you can say, suppose the diagram is, all diagrams have a definition, have a mathematical definition, if they have less than n internal edges. And then you add an extra internal edge, and then you define this diagram by saying, okay, let's cut up this edge, and you get, for instance, two diagrams. You can also have them connected if you want. But suppose that you can cut it and you get two diagrams, and you have this Q. You put on this Q here, and you put on the same Q there. And Q is a Hermitian matrix, n by n. And you integrate over all Q's. So kind of, that's exactly what you do in random matrix theory. Yeah, you can also derive actually this definition from really an action principle in the sense of random matrix theory. And I also want to stress the link with the Grosse-Ruckenaar model, this approach to non-commutative quantum field theory. It's what people call non-commutative quantum field theory. But that is, up to now, what we know is just 5 to the 4th, or maybe a few others, but especially 5 to the 4th, which is like a toy model in physics. Yeah, of course, a very important one. And this Grosse-Ruckenaar approach really works out renormalizability of this non-commutative version of 5 to the 4th theory, which is a huge result. So yeah, that has inspired many researchers to work on that, and inspired also physicists to come to non-commutative geometry. So I think that's really a good reason to do what we are doing, because what we are doing is kind of the same thing, but we are using the spectral action as our starting point. And what that means, the spectral action has all these different interactions with arbitrary valence vertices. All right, and then yes?
I have a question. I'm a little bit lost. So n here is a natural number, capital N, yes? And it is
yes,
fixed, yes?
Yes.
And your Dirac operator is a finite dimensional matrix, or?
No, but you restrict to the, yeah, you can say D is finite dimensional, but you can also say D is self-adjoint unbounded, but you restrict these Qs to the first n eigenvalues. So the, yeah, you have this, this subspace of H, this n-dimensional subspace of H given by the eigenvectors of D up to n.
Mm-hmm. So we consider this truncation, and then n tends to infinity, yes?
So you see infinity?
No, you consider this truncation, and then you let n go to infinity, yes?
Yes, 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 yes.
Mm-hmm.
But the problem here, as always in quantum field theory, is that the limit is not finite. So it blows up as n goes to infinity. So n is kind of to keep track of that. How fast does it go to infinity? And the purpose of renormalization is actually to wind up with something that is actually finite if n goes to infinity. And that's what this thing is. Mm-hmm. So this thing, yeah, should in fact be finite eventually. But for now, we're just looking at the one loop case. So we sum over all relevant one loop, one particle irreducible endpoint functions. And then it's a result. Yeah, I have to define what relevant means. It means exactly that it blows up as n goes to infinity. So you can really, this is really like how you distinguish diagrams, like which ones blow up as n goes to infinity and which do not. And the ones that blow up as n goes to infinities, these are the infinities that you have to subtract from the original one. So it turns out that those things are exactly the planar ones. The planar ones, and those can be written in the plane with edges cyclically extending outwards. So you can actually define this thing. And then we say that the one loop quantum effects in spectral action is given by this formal series. And now we can derive this of this new bracket, like a sort of quantum bracket at one loop. We can see, yeah, you can expand it as all these diagrams with one loop, and these gauge fields can be attached in any way. So use your imagination. Like this can be attached in any way you like, and yeah, arbitrary amount of vertices as well, but they are all in the plane. So that's the first thing you have to derive. They can all be written in the plane. And these are precisely the ones that blow up as n goes to infinity. So the ones that you want. And if you look at this, then you can see that by definition, this is cyclic, because we have just said that we have defined it like putting on the V's clockwise. And then the question is, does this word identity for this bracket, this new bracket, hold as well? So if you commute, if you put on an A on the left of this V2, does it come out on the right of the V1 as well? And the answer now, I will be very brief, is yes, it does. And I refer to our paper, our last paper, for the proof of this. But it's nice, you can do it completely diagrammatically, or you use a little bit of graph theory. And what this means, so we have this these two properties of the brackets, and those were exactly the ones that we needed to find cyclic cocycles and to find this expansion in terms of Chern-Simons and Yang-Mills. These are the only properties that you need. So an immediate consequence is that you have this asymptotic expansion in terms of Chern-Simons forms and powers of the curvature, where you integrate over some cyclic cocycles. And these cyclic cocycles are new ones. You can expand them in terms of diagrams. You can write them as like a sum of diagrams. But what that means, we have actually obtained this like correcting cyclic cocycles, which indicates that indeed maybe there is some renormalization flow taking place at the spectral level. So really without giving up on the beautiful nature of spectral geometry. So there are still a lot of things to do. So yeah, I hope that we get to do them, and we get to get many collaborators who also want to work with us on this. So hopefully more functional analysis and more loops to follow in the future. Thank you for your attention.
Thank you very much. Your beautiful talk.
Yes.
Any questions or comments?
I have one. Yes, I mean, it seems to me that, then when you say more functional analysis, more loops to follow, I would also like to see the Hopf algebra.
Yeah, of course. Yeah.
Yes.
Yes, certainly. Yeah.
And try to understand behind all this, what is really going on with renormalization. This would be my hope, really. Because after all, what I have in mind is that, with the, when you do renormalization, do you plan to use, I don't know, dimensional regularization or something like that, or?
No, at this point, no.
No. So how do you control?
If this n, you have the eigenvectors. Yeah, you have.
Yeah.
Yeah, you use this n as your regulator.
Yes, you want to use n, as a cutoff parameter. You mean essentially?
Yes, yeah.
Yeah. So it's very much like the Wilson point of view rather than.
What point of view?
Wilson.
Yeah.
Yeah, I see. So you mean like renormalization flow and so on. Okay, so it's less algebraic. On the other hand, okay, the advantage of the algebraic way is that, this algebraic stuff should fit together very, very well.
Yeah.
So in a way, it would be good to have perhaps some variant of that which uses a different process than the n going to infinity. Of course, the n going to infinity is quite nice because you can compute with random matrices. So that's a very good. I see. Yes. But anyway, I mean, it's a very really impressive result. I mean, this one loop business, I mean, it's amazing.
Thank you very much.
Yeah.
Yeah, I wouldn't know how to do dimensional regularization if it helps in any way, because
Yeah, well, one would have to think, you know, in the ordinary case, how you pass from the kind of, you know, finite approximation to the dimensional one. And I don't know where to read about this, but yeah, I mean, because of course for the Birkhoff decomposition, one needs the dimensional regularization. So, I mean, then you are really in pretty good waters because you have a conceptual framework. But already, I mean, the fact that, you know, there is this cyclic cohomology entering, I mean, that gives a very good.
yeah, you would expect some Hopf algebra to come out. Yeah.
Yeah, exactly. To mix with that. I mean, you know, the Hopf algebra would encode the renormalization steps.
Yes.
Whereas the cyclic cocycles would give you the stage somehow, you know, where things happen. But what I find really amazing is that you have a cyclic cocycle both for the Chern-Simons and for the curvature, which is an amazing thing, really.
Yeah.
Further questions?
I mean, classically, these Chern-Simons transgress powers of F. So differentials of Chern-Simons turn out to be F to the K for different Ks. So I guess this means, yeah, this perhaps is behind it being closed. Your cyclic cocycle is really cyclic cocycle. You know what I mean?
What do you mean by closed?
Well, I mean, because the Chern-Simons that you wrote in the universal picture, I mean, I think D of CS2K minus 1 is going to be FK in the universal picture that you introduced in first part. Isn't it?
Good question.
I mean, D of CS3 would be F2 and things like that. Because you are in a universal picture, it looks like you are in the total.
Masoud, it's not true for D of CS1. I mean, D of CS1 is just DA.
Yeah.
DA plus A square.
Oh, it's DA, okay.
Right. So it's not DA plus A square. No. This.
Yeah, you are right in the commutative case, right? You are.
Right.
Yeah, but something goes on here.
No. There is.
I mean, yeah. Sorry, this is the
maybe even for like Leo's valued it already.
No, I think I know that the correct statement is if you take two different connections, then the corresponding
then you have to do
Chern classes. The difference between the two transgresses by Chern-Simons. I think that's
sure. But this is the integral formula essentially.
Yeah. This.
Yes.
Yeah.
Okay. Yeah, I have a crazy suggestion about the Hopf algebra.
Okay.
Yes.
Namely, the gauge group, which is behind this, Masoud was asking at the beginning, is the unitary group of the algebra.
Yes.
I mean, acting on the vector potentials.
Yes.
So this is the analog of GLN. So the Hopf algebra could be forms over that, like Gorokhovsky's, you know, Hopf algebra, and its Hopf cyclic cohomology could be involved in this.
Well, except that the Hopf algebra that you get in the ordinary renormalization picture is really coming from the graphs.
I know, but
yeah, but the graphs don't. Well, okay, I don't know. Yeah.
We are not sure yet to get out of Hopf algebra because the
yeah.
Like if you take all these vertices to be just points.
Well, but I'm saying it because we had that chain character, interpreted in terms of equivalent construction and stuff like that. That was related to GLN being GL infinity of the algebra.
That's true.
Okay, so
That's true.
but
But
with the
here,
Hopf algebra, then you will get the cyclic homology for that, something like that.
there is one indication which goes in a slightly different direction, which is that your graphs at the tree level have the index f, where f is this function. Always. You always have the f.
I see.
The Hopf algebra should involve the f, should depend on f somehow. Because at the tree level, it uses f.
Mhm.
It's very hard to, and then it should connect, as Riku was saying, it should connect with the algebra, but it will connect in a kind of semi-direct product way. I mean, not because the Hopf algebra is something very universal, which depends on the combinatorics of the graphs more than anything else. I mean, it's really something which is combinatorial. It sort of subsumes the combinatorics of the graphs. I mean, that's what it does. Not more than that, actually.
Could I just give one example of a
Sure.
graph that's really problematic in this way? It's kind of problematic into giving a Hopf algebra in the way that you would expect it, because you have this graph, for instance,
which is not the same as the other one where you permute the two.
which is not,
Sure.
and it's
Well,
also
okay.
not the same as this one.
I understand. Yes, sure.
Yeah.
Because of cyclicity. Yeah, but okay, fine. I mean,
But this was
more.
kind of comes from this thing, but it comes from this thing in two ways, whereas this one comes from that one in just one way, because you can contract the middle loop, but you cannot contract the outer loop.
Yeah. Okay. Sure. No, I understand very well. But okay, what it means is that the combinatorics is more involved. I mean, that's what it really says.
Yes. Yeah, it's not so clear yet to me. But,
No. It was just a suggestion, and
yes.
what I mean is that what is going on is that more and more of the pieces of the physicists, which look at first totally ad hoc and so on, and not rigorous and so on, they acquire mathematical meaning, but it seems to be always the case that the mathematical meaning is the most subtle one. It's not at all the one that one would guess from what they are doing. I mean, so I mean, for the spectral action, it's a marvelous fact that I mean, the goal would be then to understand how the renormalization group is acting on the non-commutative geometry, and to follow the renormalization group on the non-commutative geometry, of course. I mean, that's really the ultimate
the ultimate goal.
Yeah, ultimate goal.
Any further questions or comments? I see that you missed the sunrise turn. Sorry about that.
Yeah. But you didn't.
It's sunrise.
You have followed the sunrise.
Well, they're
That's
lucky
right.
they're in the spring, these guys, so.
Yeah. It's gonna be
Well,
a good day today.
it's going to be a good day, I'm sure it is. And thank you so much for your lecture this morning. Thank you so much for getting up and out of your pajamas at such an early time. We shall resume the seminar, I think, in 2 weeks. Hope to see as many of you as possible then. Thank you and goodbye.
Thank you. Bye.
Yeah.
Thanks, Teun, for a very nice talk. Thank you.
Thank you.
Thank you very much.
Thank you.